All right, let's dive in. For the longest time, the race in quantum computing seemed pretty simple. Who could build the most qubits? More was always better. But the whole game is changing. We're going to explore a huge shift in how we measure progress. We're moving from just counting qubits to chasing something way, way more powerful: quality. And to get us started, here's a little riddle for you. How on earth can 100 be greater than a million? I mean, in the quantum world, how can a computer with just 100 qubits actually be more powerful than one with a million? Sounds totally backward, right? Well, stick with me, because by the end of this, you'll see how that's not just possible, it's the future. Okay, so first things first. Before we get to the answer, we have to understand the massive, fundamental problem that every single person building a quantum computer is wrestling with. We are building these amazing machines on a foundation that is, well, it's incredibly shaky. We've all heard the incredible promises, right? New medicines, unbreakable cryptography, new materials, the list goes on. But the catch, and it's a big one, is that the building blocks themselves, the qubits, are unbelievably fragile. They're like tiny little divas. Any little vibration, any stray bit of heat, what we call noise, can knock them off course and destroy the calculation in a split second. This process is called decoherence, and it's public enemy number one. And this right here really gets to the heart of it. On one side, you have the ideal qubit you read about in a textbook. It's perfect, it's stable, it never makes a mistake, it's the dream. But then on the other side, you've got reality, the physical qubit we actually build in a lab. And it's messy, it's noisy, it makes errors all the time. So the grand challenge is, how do you build a reliable computer out of unreliable parts? So if your building blocks are basically made of sand, how in the world do you build a skyscraper? Well, it turns out there's this brilliant idea, a concept that's absolutely central to making any of this work. It's called quantum error correction. The whole idea behind quantum error correction, or QEC for short, is basically safety in numbers. Instead of entrusting your precious piece of information to one single fragile qubit, you spread it out. You encode it across a whole team of physical qubits. That way, the team can constantly check on each other, find any errors that pop up, and fix them on the fly, all while protecting the original information. Let's look at a simple example to see how this works. Say we want to protect a qubit that's in the zero state. Instead of just one qubit, we use 3, and we put them all in the zero state. So 0 becomes 0, 0, 0. Now, let's say some random noise comes along and flips that middle qubit to a 1. Our state is now 0, 1, 0, which is wrong. But here's the genius part. We can do a measurement that asks the group, hey, is everyone here the same? This check, called a syndrome, tells us that the middle one is the odd one out without actually destroying the quantum data. Once we know who the culprit is, we just flip it back. Boom, information saved. Now, that's a neat trick for a simple error. But real quantum algorithms can be millions of steps long, and there are way more complicated errors than just a simple flip. So to make this work for real, you need more than just one trick. You need a whole toolbox of advanced techniques to build a truly fault-tolerant machine. One of the most important tools in that box is called the surface code. Honestly, the easiest way to think about this is like a blueprint, an architectural plan. You arrange your physical qubits in a 2D grid, just like a checkerboard. This layout is so powerful because it means error checking is simple and local. Qubits just need to check in with their immediate neighbors. It's a much more practical way to build and scale these systems. Okay, but some of the most powerful quantum operations are too tricky for even the surface code to handle directly. For those, you need special resources, a kind of high-octane fuel. And that's where another tool comes in: magic state distillation. It's basically a purification process. You take a whole bunch of noisy, low-quality states, you run them through this distillation protocol, and you get a much smaller number of super pure, high-fidelity states at the other end. These magic states are what you need to unlock the full power of the computer. So all this amazing work, the teamwork of error correction, the checkerboard layout, the fuel purification, it's all been leading to one thing. It's all in service of creating the real star of the show. And here it is, the logical qubit. Now, the key thing to understand is you can't go into a lab and physically point to a logical qubit. It's not a thing, it's a concept. It's this new, stable, robust unit of information that emerges when a whole team of those noisy physical qubits works together, constantly running those error correction plays we just talked about. This quote from the Quantum Insider just nails it. The key word here is imitate. A logical qubit is a group effort where hundreds or even thousands of physical qubits all work together to perfectly imitate one of those ideal, flawless qubits that we dreamed about at the beginning. It's a tough, digital entity built from fragile analog parts. And this right here, this brings us right back to our riddle. This chart shows you the incredible overhead we're talking about. Depending on the type of physical qubit you're using and how noisy it is, it can take thousands, literally thousands, of them just to create one stable logical qubit. And this is how 100 becomes greater than 1,000,000. A machine with 100 high-quality logical qubits can run circles around a machine with 1,000,000 noisy physical qubits that can't even finish a calculation about errors. It is all about quality over quantity. So this realization has caused a massive shift across the entire quantum industry. It's a totally new ballgame. The race isn't just about building the biggest quantum computer anymore, it's about building the smartest one. Yup, the goalposts have completely moved. The key metric that everyone cares about now isn't the raw physical qubit count. That's old news. The new benchmark, the number that actually tells you if a machine is useful or not, is the number of high-quality, error-corrected logical qubits it has. And hey, you don't have to take my word for it. Just look at the public roadmaps from the big players in the field. Companies like Pascal, Quantinuum, IQM, they are all explicitly stating their goals now, not just in terms of physical qubits, but for the logical qubits they expect to build. That's the number they're staking their reputations on. And this isn't just some corporate marketing fad. You can see the same trend deep in the actual science. I mean, look at this timeline. The number of research papers and patents that even mention the term logical qubit has absolutely exploded. This is where the real work, the fundamental R&D, is happening. As you look across all this research and all these roadmaps, a particular number starts to pop up over and over again, 100. Achieving 100 stable, working logical qubits, that seems to have become the next great milestone for the whole industry. It's the goalpost that marks the beginning of a truly new era in computing. So why is that number so important? What's so special about 100? Well, get this. Researchers estimate that a quantum computer with as few as 49, not even 100, just 49 logical qubits could perform simulations so complex that they're just impossible for even the biggest supercomputers we have today. 100 logical qubits would blow the doors wide open to new discoveries. So there you have it. The whole quest for a quantum computer has evolved. It's not a race for sheer size anymore, it's a race for sophistication. The goal is to build a machine that's smart enough and stable enough to finally start solving some of those impossible problems we face. And with that milestone of 100 logical qubits now clearly on the horizon, it just leaves us with one incredibly exciting question. What are we going to discover first?